Our next speaker is Adrian Tanasa from the Max Planck Institute in Bonn. And he will speak on the Connes-Kreimer Hopf algebra. That's this same general theme, but this time for non-commutative field theory. So I guess you're going to do it without a computer. So
yeah. Well, actually, when Malek invited me to this conference, I thought that there would be mostly mathematicians, so everybody will speak at the blackboard. So now I arrive here, and all the mathematicians use the computer, and I have to speak at the blackboard. So this.
Use the blackboard now. So physicists are going to use the blackboard.
The blackboard, yeah. So this talk is based on a joint work with Fabien Vigne-Tourneret on a paper which is published in Journal of Non-Commutative Geometry, and on some recent results I'm currently working with Dirk Kreimer. So I'm going to start by introducing what physicists understand by Feynman graphs and say a few words about quantum field theory. Then we will see how all this uplifts to non-commutative quantum field theories. These are topics which were covered also in the talks of Vincent Levasseur and Răzvan Gurău here, but I'm just going to reintroduce some of the notions that will be useful for the sequel. Then I'm going to present the Connes-Kreimer algebra for commutative quantum field theories, as was presented in the previous talk, but in a manner that will be easier for me to present the last part, which is this Hopf algebra construction for non-commutative quantum field theory renormalization. So when we talk about quantum field theories, a general notion for physicists is the so-called Feynman graphs. So I'm going to use the 5-4 model, which you saw in the talks yesterday also. So for example, a very simple Feynman graph is the following. One has this line, which is called a propagator, and this thing, which we call a tadpole. So there are particles associated to the propagation of these lines. So for example, one has a momentum p. To each vertex, we associate a coupling constant, which is denoted by lambda. So the Feynman integral associated to the Feynman graph here, in this example, we simply write in the following way. So we integrate on this variable p associated to each internal line, and the propagator for this line in this 5-4 theory writes in this way. So we have this type of integral. If one can consider a more and more complicated Feynman graphs of this way. So for example, if I consider a Feynman graph like this, this time we have two internal lines, so we have to integrate on these variables, and since we impose conservation at each vertex, we impose conservation of these momentas. The two variables will be dependent. So at the end, one can write, since we have now two vertices, lambda squared. So the Feynman graph associated to this writes in the following way.
What's M?
Oh, M is what we call the mass. So maybe I should write the action. So what we call the action for this model So, as you saw in the yesterday talks, we have what we call an action. So we have this part is called the propagation. Which translates itself in the expression of the propagator for each internal line. And this part is called the interaction, which expresses in the fact that in each vertex here, so we have a 5-4 theory, we have 4 lines entering or exiting the vertex. As you can see, these integrals, the examples I gave here are divergent. So this is a crucial thing in quantum field theory, because one has to get rid of these divergences via a process which is called renormalization, if this process is possible. And an important notion is the power counting, which is roughly speaking counting the number of powers one has in the integrals of the momentum. So the number of powers on the numerator and denominator, and to see whether or not the integral will be divergent or convergent. So one can prove that for this 5-4 commutative model, this degree of divergence, which is usually denoted by omega, it's proven to be equal to n minus 4, where n is the number of external legs. So for example, here one has 2 external legs, and here one has 4 external legs. So the more this number is positive, the more the integrals will be convergent, and the more it's negative, the more the integral will be divergent. So for example, here, the number of external legs is equals to 2. So this power counting will give us the result minus 2, which shows us that this integral is divergent, as one can directly check. And here, this power counting leads to a superficial degree of divergence equals to 0, which shows also a logarithmical divergence of the integral. When one does the renormalization of quantum field theory, as was presented by Vincent Rivasseau, one way of seeing this is the disentanglement of a graph in primitively divergent subgraphs, as we saw also in the previous talk. So these primitive divergent subgraphs are the graphs indicated by this power counting calculus. So in this case, the primitive divergent subgraph will build a graph with 2 and 4 external legs, like for example these 2 little graphs here. So when one tries now to go to non-commutative quantum field theories, the way of introducing this non-commutativity comes from physical reasons, and it's based on what is called the Moyal product, which I'm going to write here. So this implies non-commutativity matrix theta, which has the following way, which is written in the following way. And one replaces the usual commutative products between the phi and the x fields with this non-commutative star product. So one will have star products everywhere in its action. So as we saw yesterday, there is a property of this Moyal product which says that at the level, if one has only 2 elements integrate in the section, the Moyal product, so the Moyal product can be just forgot about. It's the same result as the point-like product. So, as Vincent Rivasseau was saying, this can be seen like the property of cyclicity. Since we have only 2 elements, then it's the same thing as the permutation. But the interaction part will be highly different from the point-like interaction before. And one can prove that this interaction part, so by phi star power 4, I understand phi to the power 4, but with a non-commutative product star at the place of the usual multiplication. So this form of the 5-4 interaction leads to the explanation to the fact that one can represent this vertex from the commutative field theories under non-local form, like here, with the 4 incoming and outgoing fields. So, moreover, one does not have, if here one had a permutation of all the 4 incoming and outgoing fields, this is now replaced by a permutation only under, invariance only under cyclical permutation. So this leads to the idea of representing this graph using ribbon representation, and not anymore drawing lines like was the case before. This form of the non-local interaction leads to a clear distinction between planar and non-planar graph. So what do I mean by this? For example, if I was considering the example of this tadpole graph over there, I can draw it in the commutative case in this way. Now I can do this in the non-commutative case in this way, which is a trivial generalization of the commutative case. But since the vertex here is now non-local, one can draw the tadpole in this non-planar way, which we refer to also the non-planar tadpole. And now when we compute the Feynman amplitudes by generalizing these Feynman rules we had for commutative quantum field theories, one can prove that for the planar graphs, the calculations are follow more or less the same rules as in the commutative case. But for this new type of graphs, for example, for this non-planar tadpole, if one writes down the Feynman amplitudes as in this case, one proves that we have a divergence as 1 over p squared for small values of p, where p was the external momenta here. So this type of new divergence, which is called mixing, ultraviolet infrared mixing, cannot be absorbed in a redefinition of the parameters of the action. So therefore, in this sense, the theories are non-renormalizable. So the situation remain like this until the modification of the propagation by the introduction of the following term. This famous x squared term, which was mentioned yesterday also. By two physicists, Harald Gross and Raimar Wurkener. So introducing this new term, it was proven that the model becomes perturbatively renormalizable. So before going into more details, let me just give some notions of topology on these ribbon graphs, notions that we use for this type of calculations. So one of them is the Euler characteristic, which gives a relation between the genus of the graph G and the number of vertices n, the number of internal lines L, and the number of faces F. So for example, if I take a graph like this, so n is the number of vertices, little n. So in this case, it's equal to 2. The number of internal lines, L, is equal to 3. And the number of faces is obtained in the following way. So here we have one face here, a second internal face here, and some kind of an external face on the outside, F3. So without crossing the lines. So if we input these numbers into the general relation given here, the genus of the graph is equal to 0, which corresponds to planar graph, which is obviously the case for this figure. Moreover, there is another notion of what we call broken face, the number of faces which are broken by external lines. So in this simple example here, The only phase between these three, which is broken by external lines, is F3, obviously. So one says we have one broken phase, B equal to 1. Since we deal with these non-local interaction vertices, one can switch, for example, the endpoints of these internal lines, and we can thus obtain an example of a non-planar graph. So there it is. So as before, we have two vertices. We have three internal lines. Nothing has changed. But now, if we do this counting of number of faces as before, we can find out that we have only one internal face. So now the number of broken faces will be trivially found to be equal to 1, since we have only one face. Inserting now these three numbers into the general relation giving the Euler characteristics, one finds the genus of the graph equal to 1, which corresponds to the fact that this graph is non-planar. So G equals to 0 corresponds to planar graphs, and G superior to 0 corresponds to non-planar graph. Okay. So if we now want to establish the result of the power counting, which in the case of commutative phi 4 was equal to this omega superficial degree of convergence was equal to n minus 4. In this case, the situation is more involved. So one can prove using various methods, which I'm not going to enter into details here, that this superficial degree of divergence is equal to n minus 4, as before, plus some other contributions from the genus of the graph, as shown here, and from the number of broken faces, as also defined on this blackboard. So I was saying that crucial for the process of renormalization were what we call the superficial divergent graphs, which are given by this power counting. So in this case, the superficial divergent graphs will be again the 2 and 4 external legs graphs, but supplementary conditions imply that the genus has to be equal to 0, and the number of broken faces has to be equal to 1. So we have to deal with planar graphs which have only one broken face. So we have chosen to call these graphs planar regular graphs. And it is them that run the process of renormalization. I was also mentioning before the fact that one can express the process of renormalization as a factorization issue by disentanglement of a graph into using this, looking at the subgraphs which are primitively divergent, given by this power counting. So one can see this in an elegant way using the parametric representation that we saw in the talk of Răzvan Gurău. So if I denote the amplitude of a graph gamma by phi, it was proven that this integral can be written using this parametric representation in the following way. So these are the two polynomials HU and HV that was shown to you yesterday, and T are some parameter for each internal line L from 1 to big L. One has a parameter T, and one can express the Feynman amplitude in this way. If one considers now a subgraph gamma, little gamma, which is a subgraph of big gamma and is primitively divergent. So I will use this notation with underlining of gamma by meaning subgraph, primitively divergent subgraph of gamma. In a paper where we have looked at the dimensional regularization of this type of models, we have shown the following results. If one rescales with some parameter rho, the parameters t associated to the lines of this subgraph gamma, then, for example, one has an interesting property of factorization of these two polynomials. So I'm gonna write down the one for the first polynomial. So by this index L, I meant the leading terms under this rescaling with the parameter rho. So the total polynomial of the graph gamma is explained, the leading terms are expressed as a product between the polynomial of the subgraph little gamma, its leading terms, times the polynomials of the total graph big gamma with the little graph gamma shrink to a point. So this is what I understand by this gamma over gamma notation. So let me give an example by what I understand by this shrinking.
Is it the leading term too, or it's the full?
Plus subleading.
Plus subleading, but here I just wrote this identity. These are just the leading terms.
No, the guy on the right, is it the leading term of this polynomial, or the full?
This one is the leading term, and this is the full polynomial. So let me give an example. So if my big graph gamma will be this graph, I was saying that the primitively divergent graphs are the 2 and 4 point planar regular graphs. So for example, such a primitive divergent graph little gamma will be this one. This is a 2-point function. So I'm just going to shrink it. So since I want to keep the number of external legs the same, I'm going to obtain this, where this was this came from the shrinking of this subgraph. So by an explicit computing of these polynomials, one can prove that the HU polynomial of the total graph here, its leading term under this rescaling are written as HU polynomial of this little graph, its leading terms, times the polynomial of this graph. And this we have proven that this is a property which remains valid for all kind of graphs, and it also extends to the level of the second polynomial HV here, but in a more complicated manner, on which I am not going to insist here. So this property of factorization is very important for defining a Hopf algebra structure. But before doing this, let me just say one more thing. That we have seen that by adding this x to the square term, we obtain a perturbatively normalizable model. Well, lately we have proved in a recent paper with Răzvan Gurău, Jacques Magnan, and Vincent Rivasso, that one can write a different action, we call it S', where in the space of the momentums P, which are the Fourier transformation of the position x, so what do I write here? I wrote that this phi 4 action in the momentum spaces, and I have added a new term on 1 over p squared. So this term on 1 of the p squared can be seen from the fact that when one computes this non-planar tadpole here, we are obtaining a 1 over p squared divergence. So we can just add this to the propagator, And we have proven in the paper I have just cited that this model also is perturbatively renormalizable. So the power counting that we obtained here was bounded by the following numbers. So for planar graphs, it will be the same 2 and 4 point planar graphs. And then for non-planar graphs with genus superior to 1, the graphs will be convergent. Moreover, for the graph with g equals to 0, n equals to 2, but with more than one broken face, we have proven that all the graphs have this type of behavior, 1 over p squared, which is actually finite, because p it will be just the external momenta. The divergence will come when inserting this type of tadpole graphs into bigger graphs, which are non-planar, and then they will become divergent. But thanks to this modification of the propagator, this graph will be also finite because of this new term. Moreover, one can argue whether or not this type of modification can extend to non-commutative gauge theories. So the conclusion for this will be that also the planar regular graphs are the one which have a crucial role in the renormalization, just with the case of the previous Gross-Vulkenar model. So let me finally go through to the presentation of the Connes-Kreimer algebra. So we take H to be the algebra generated by the Feynman graph, just as we saw in the previous talk. And the most important operation is the coproduct, which drives the combinatorial aspects of renormalization. So as we saw for some graph gamma, this coproduct has a trivial part. Where one is the empty set, and this, as before, was a primitively divergent subgraph of gamma.
What is the grading here?
The grading is the number of loops, just as in the commutative case. And so the rest of the operation are defined in the following way. So the co-unit is defined as being non-trivial for the trivial graph, for the empty set, and being trivial for any non-trivial graph. And the last operation to define is the antipode S, which is defined recursively. So with these operations, Connes-Kreimer proved that for commutative quantum field theories, this coproduct and these operations lead to a Hopf-algebra structure Feynman graphs. So in order to extend this to the non-commutative case, let me write down an interesting result. So, but first let me give an example how this, so if I call this non-trivial part of the coproduct delta prime, this being the trivial part, let me just give an example to see how this thing works. So if I apply the coproduct defined on that blackboard on this graph, so now I'm in the commutative case. So these are just usual vertices and usual propagators. So the primitively divergent graphs, subgraphs will be given by this each of the loops I can obtain here, because there will be two-point function. So I will have, this will be my little gamma times what I obtain by shrinking this to a point. So in this case, it will be this start point. So this will be taken into consideration 3 times, because I can have three ways of counting these loops. So I was saying that before I'm going to announce some result that for defining this Hopf algebra. So the result is the following. So if the conditions 1 and 2, whereby 1
Do you want to extract 3 loops or 2 subdivergencies?
Sorry?
You have 2 overlapping subdivergencies, right?
Yes.
But you extract 3 loops. Is this the right counting?
What
The
do you mean?
grading, you have the grading in terms of loops, but you want to extract subdivergencies, right? Because you have
Yes.
only 2 overlapping.
Yes.
So if you apply the Bogoliubov recursion, for instance, you would extract only 2
Yes.
subgraphs, but you have 3 extracted there. Is this the right counting?
Yes, because I have three possible loops.
But I have only 2 subdivergencies. If you apply the Bogoliubov recursion, you would only 2.
Yes, but for the moment I'm just applying with this definition.
Okay.
So okay, so this lemma says the following. So if these 2 conditions are satisfied, namely, if one has two subgraph, gamma and gamma prime a subgraph of gamma, which are primitively divergent, then gamma with gamma prime shrinked are primitively divergent. And the second one, for any gamma 1 and gamma 2 primitively divergent, there exists gluing data G such that gamma 2 glued into gamma 1 is primitively divergent. So I'm going to write down what I mean by this. Then the coproduct defined in this way is co-associative. So what do I mean by this gluing process? So for example, if I have a graph gamma 1, like this, and another graph gamma 2 which writes like this. So for example, I can glue this graph gamma 2 inside. So this is a 4-point function, so it will be glued, for example, in this vertex here. So one will obtain something like this. And the number of external legs of the initial graph gamma 1 will be preserved by this gluing operation. So this means that G1 with gamma 1 with gamma 2 glued in will be also primitive divergent, since in the commutative case this primitive divergence was given only by the number of external legs. So one can easily prove that this number of external legs will be conserved by any type of gluing of 2 or 4 point graphs. And one can then prove that if this, as I was saying before, that if these two conditions are satisfied, then the coproduct defined in this way is co-associative, which is requested for the proof of the theorem that all this structure is a Hopf algebra structure. So in the case of commutative field theory, any gluing data satisfies this because one has a point-like interaction. So let us see how we extend this to the non-commutative case. So to the non-commutative, for non-commutative quantum field theories, the formal definitions remain the same. One defines the coproducts in the exact same way, only that the sum now is done on as before on the primitively divergent subgraph, but this time the primitively divergent subgraphs were, as I was saying, well, I think I raised it, the planar regular graphs. So in order to prove that this structure will also remain a Hopf algebra structure in the non-commutative case, we want to prove these two conditions. So the first one says that if one has a primitively planar regular 2 and 4 point graphs and takes a subgraph which is also planar regular and shrinks it to a point, the result will be a planar regular. So this is immediate, since by shrinking a planar part of a planar subgraph of a planar graph, the result will also be planar regular. The more tricky case will be when one tries to glue graphs into graphs in this way. So if one wants to glue 2-point graphs, which are planar regular, the situation for 2-point graphs, the situation will be immediate again, because this will be inserted at the place of a propagator. So if this will be planar regular, the result will also be planar regular. The situation is slightly more complicated in the case of a 4-point graph. So if one has this type of moral vertex, and decides wants to glue some kind of a subgraph, as was done here. So let's So what has to do is to take gluing data, which takes into consideration the fact that the symmetry and the permutation is lost, but is replaced with this permutation and this symmetry and the cyclical permutation. So for example, here the things will be okay, but if one glues a 4-point graph into a moral vertex in this way, then obviously the result will not longer be a planar regular graph, since the number of broken faces of the genus will increase. So if before in the case of commutative field theory, any gluing data will satisfy this condition, in this case, only gluing data which preserves this restrictive symmetry can satisfy the theorem. So let me give an example before ending. Let me give an example of this coproduct applied on that graph, which are now Rubin graphs. So in this case, one obtains what we call the up tadpole, down tadpole, and the non-planar tadpole. Since these three tadpoles are no longer equivalent, since we deal with Rubin graphs anymore. So with this, I thank you for your attention.
Well, we have time for questions or comments.
Can you formulate the Birkhoff decomposition in?
So it keeps the exact formulas that you showed in your talk. The Birkhoff decomposition remains exactly the same. Since the only difference is that the primitive divergent graphs are the same, but the formal definitions are exactly the same.
It's not that this non-commutative version includes the commutative version, right? So there's not like one can see this as a generalization of one Hopf algebra of the other, right?
No, I won't say that. The non-commutativity translates in the fact that the graph are Rubin graphs, so one has to take care with things like this or things like this, but the formal definitions are the same, and yeah, I don't think I mean it's an extension. The algebra is still commutative, so the multiplication of the product of the Hopf algebra is the same, and it's commutative. The non-commutative is just translated into these Rubin graphs. So one can see the generalization in this sense, but in a mathematical sense, I won't say so.
Is there a way to continuously deform the Hopf algebra into another? By introducing more parameters?
This is an interesting question. Maybe if,
It's a bit the same question. In fact.
yeah, it's
In a different
related to
guise.
this question. Yes. At the first sight, I won't have a positive answer like this, but maybe if one looks more carefully, maybe.
Because, for instance, at the level of polynomials, we saw yesterday that it is possible to deform this polynomial into
the commutative
into
one.
the Kirchhoff, yeah, into the ordinary.
The thing is that here one has this information on broken faces and genus of the graph, so one has to come back to the previous case. So I don't know, maybe this can be done, but I don't have something in mind.
All right, let's take a 2-minute break. Thank the speaker.